telescope image seems like it should show a single moment, frozen and clean, as if the universe paused long enough for us to look. But when James Webb turns toward deep space, that simple idea begins to fall apart. The light in one corner may have crossed a quiet region of space for a few thousand years, while another faint smear may have been traveling since before the sun existed, before Earth had oceans, before there was anything here that could look back. Webb is not only photographing places, it is catching different ages of reality as they arrive together, and that means the sky is not a still picture. It is a delayed conversation with time itself. If you enjoy calm, science-rich journeys like this, stay with me and consider subscribing. Now, let's begin with something familiar, the feeling that a photograph means now. When you take a picture of a city street, you know what it means. A bus is passing, someone is crossing the road. Light bounces from those things into the camera, and a fraction of a second later, the image exists. Even if the photograph becomes old, the moment it captured was local, immediate, human. The delay was too small to matter. The universe does not give us that luxury. Light has speed, and because light has speed, distance becomes memory. The moon is about 1.3 light seconds away, so we never see the moon exactly as it is. We see it as it was just over a second ago. The sun is about 8 light minutes away, so sunlight on your skin is already 8 minutes old when it arrives. That delay feels small, almost poetic, but it is the beginning of a much larger fracture in intuition. Once you leave the neighborhood of Earth, now becomes harder to define. Once you look across galaxies, it almost disappears. This is the first quiet shock behind Webb's view of cosmic evolution. The telescope is not watching one universal present. There is no single clean now spread across the cosmos like a sheet. There is only light arriving from different distances, each distance carrying its own timestamp. The deeper Webb looks, the older the light becomes, until a faint red galaxy is not merely far away. It is a message from a time when the universe itself was young. That's why the phrase cosmic evolution in real time has to be handled carefully. Webb has not filmed a galaxy changing shape over a few months like a flower opening in a time-lapse. Galaxies are too large, and their lives are too long, for that kind of change to unfold on a human schedule. A single rotation of the Milky Way takes roughly 225 million years. A massive galaxy merger can take hundreds of millions or even billions of years to complete. Human history is only a blink beside that. But Webb has captured something just as powerful, and in some ways more humbling. It has captured real evidence from many stages of cosmic change, all reaching us now. Nearby, it can see stars still forming inside dusty clouds. Farther away, it can see galaxies when they were younger, smaller, brighter, more chaotic, or unexpectedly mature. Farther still, it can detect ancient light that has been stretched by the expansion of the universe until it slips out of visible red and into infrared. Webb was built for that hidden light. Our eyes are not. Human vision is tuned to a small strip of the electromagnetic spectrum, a narrow band of color shaped by our sun, our atmosphere, and the needs of a life on Earth. To us, deep space looks dark because most of its messages are too faint, too stretched, too obscured by dust, or too far outside the colors our eyes can catch. Webb changes that not by making the universe dramatic, but by making it readable. Its great gold mirror, about 6.5 meters across, gathers ancient infrared light with a patience no human eye could imitate. Its instruments sort that light into images and spectra, turning dim photons into evidence. And evidence is the important word. A Webb image is beautiful, but beauty is not the discovery. The discovery comes from what the light has carried. Some wavelengths are missing because atoms and molecules absorbed them. Some are brighter because gas was heated until it glowed. Some are stretched because space expanded while the light was traveling. Some are bent because gravity from massive galaxy clusters curved the path between the source and us. Every faint mark is a clue. Every color is a measurement. Every distortion is a physical process with a history behind it. So when Webb looks at cosmic evolution, it is not seeing an abstract idea. It is seeing the machinery. The nearest form of that machinery begins in cold darkness. Long before a star shines, there is gas and dust, mostly hydrogen, with traces of heavier elements made by earlier generations of stars. In a quiet cloud, gravity works slowly. A slightly denser region pulls in more material. As more material gathers, the pull strengthens. The cloud contracts, the center heats, and eventually the pressure and temperature rise until a star can begin its life. From the outside, this can look like a glowing nursery. From the inside, it is a battle between collapse, heat, rotation, magnetic fields, and radiation. Visible light often cannot get through these dusty birthplaces. Dust grains scatter and absorb shorter wavelengths, hiding young stars from ordinary view. Infrared light can pass through more effectively, which is why Webb can peer into regions where stars are still wrapped in the material that made them. It does not simply show bright points. It shows the process of becoming, jets from young stars carving narrow paths through gas, heated dust glowing softly, dense filaments feeding new suns. This is cosmic evolution close enough to feel almost local, in regions like Orion, only about 1,000 or so light-years away. Webb can reveal young stars still forming inside the kind of raw material from which planetary systems may later emerge. 1,000 light-years sounds enormous, but in galactic terms it is nearby. The Milky Way itself is about 100,000 light-years across. Orion is not the edge of time. It is our own galactic neighborhood, and even there, the universe is not still. The important thing is that star birth is not decoration. It is the first visible step in a chain that eventually leads to chemistry, planets, atmospheres, oceans, and bodies. When a star forms, it begins changing its surroundings. Its radiation heats gas. Its wind pushes material outward. If it is massive enough, it will live fast and die violently, scattering heavier elements into space: carbon, oxygen, silicon. Iron, the ingredients that make rocky worlds and living cells possible, do not appear all at once at the beginning of the universe. They are made, spread, recycled, and gathered again. In that sense, cosmic evolution is not only about galaxies becoming larger, it is about matter becoming more complicated. The early universe began almost entirely with hydrogen, helium, and a little lithium. There was no oxygen to breathe, no carbon chemistry for biology, no iron for blood or planets, no silicon-rich crust beneath anyone's feet. Those elements had to be forged inside stars and released through stellar death. So when Webb studies ancient galaxies, it is also asking a deeper question. How quickly did the universe begin enriching itself? How soon did the first simple matter become the layered matter we now take for granted? That question pulls us from nearby star nurseries into deep time, because a star-forming cloud in our own galaxy shows the mechanism up close. But distant galaxies show the same story at earlier chapters. They are not just faraway islands of light. They are evidence of how quickly the universe learned to build structure, ignite stars, manufacture elements, and assemble the first great cities of their matter. And this is where Webb begins to change the feeling of the night sky. The darkness above us no longer feels like empty distance. It becomes a library where the pages are arranged by how long their light has been traveling. The nearby pages are newer, the distant pages are older, and Webb, sensitive to the faint infrared glow of ancient light, is reading pages that were sealed from human view for almost all of history. For thousands of years, the stars looked eternal. They rose and set. They returned with the seasons. Civilizations built calendars, myths, navigation systems, and monuments around them. The sky seemed like the most permanent thing humans knew. But modern astronomy has slowly broken that illusion. Stars are born, stars die, galaxies collide, space expands, light ages as it travels. The universe is not a ceiling, it is a process. Webb's gift is that it makes this process visible across several scales at once. It can look at dust where stars are forming now, in our cosmic neighborhood. It can look at galaxies billions of years ago, when the universe was already building structure on enormous scales. It can look toward the first billion years after the Big Bang, where galaxies should be young, raw, and still assembling. Then it can compare those eras, not as imagination, but as evidence. That comparison is the heart of the story. If you could somehow stand outside time and watch the universe unfold, you would not see galaxies appear fully formed. You would see tiny differences in early density grow under gravity. You would see gas fall into dark matter halos, cool, fragment, and ignite. You would see the first generations of stars begin the slow chemical enrichment of everything. You would see small galaxies merge into larger ones, disks settle, bulges form, black holes feed, and waves of star formation flare and fade. You would see growth, interruption, recycling, and loss. Webb cannot take us outside time, but it can do something stranger. It can let old light arrive in the present, carrying snapshots from different chapters of that unfolding. It gives us not a movie, but a cosmic fossil record made of photons. And unlike fossils in stone, these fossils are still luminous. A fossil in stone tells us that something once lived. A photon from a distant galaxy tells us that something once shone. The difference is that the photon has not been waiting in the ground. It has been moving the entire time, crossing space while planets formed, continents shifted, species appeared and vanished, and human beings slowly learned to build mirrors cold enough, wide enough, and patient enough to catch it. That is why a deep image from Webb can feel so quiet and so overwhelming at the same time. On the screen, a distant galaxy may appear as a small red point, almost fragile, easy to miss. But that faint point may be light from a time when the universe was less than 1 billion years old. If the universe is about 13.8 billion years old, then looking at such a galaxy is like opening a message written near the first few pages of a very long book. The ink is weak, the paper is damaged. The language is difficult, but it is still there. The reason ancient galaxies look red is not simply that they are made of red stars. Some are red because the light itself has been stretched during its journey. Space has expanded while the photons traveled, and as space expands, the wavelength of the light expands with it. A wave that once belonged to ultraviolet or visible light can arrive stretched into infrared. This stretching is called redshift, but the name is almost too small for what it means. Redshift is not just a color change. It is the travel history of light written into the light itself. Think of a sound that drops in pitch as it moves away, like a siren fading down the street. The comparison is not perfect, because cosmic redshift comes from the expansion of space, rather than ordinary motion through air. But it gives the feeling. The signal arrives altered. Its change tells you that the source belongs to a larger moving system. With distant galaxies, the stretch is so great that the light Webb captures may no longer be visible to our eyes at all. The universe has pulled it into a hidden register, and Webb listens there. This is where evidence becomes stronger than appearance. A beautiful red dot in an image is not enough to know its age. Astronomers need spectra when possible, or carefully measured brightness through different filters when spectra are not yet available. A spectrum spreads light into its wavelengths, like opening a chord into individual notes. Certain atoms and molecules leave recognizable marks. Hydrogen can produce emission lines, oxygen, carbon, and other elements can leave signatures. Breaks in the spectrum can show how much light has been absorbed by intergalactic gas. When those marks are shifted, scientists can measure how far the light has been stretched. But the timestamp is only the beginning. Once astronomers know roughly when the light began its journey, they can ask what the galaxy was doing at that era. Was it forming stars rapidly? Was it dusty? Was it compact? Was it already massive? Did it have a disk? Was it being torn by a merger? Did its light come mostly from young stars, old stars, hot gas, or a feeding black hole? Each answer changes the story of cosmic evolution, because each answer tells us how fast the universe was able to build complexity. Before Webb, many models suggested a general picture that still remains deeply useful. Small structures formed first, gravity gathered matter into dark matter halos, gas fell in, cooled, and formed the first stars. Galaxies grew through star formation and mergers. Over billions of years, they became the grand spirals, ellipticals, and irregular systems we see closer to the present. This picture was never simplistic, but it carried an expectation. The earliest galaxies should often be small, young and not yet fully organized. Some early galaxies Webb has revealed appear surprisingly luminous. Some seem to have assembled significant stellar mass quickly. Some appear compact, dense, and rich in star formation. Some may show signs of structure earlier than older intuition made comfortable. These findings do not mean cosmology has collapsed. They mean galaxy formation is more efficient, more varied, and more sensitive to environment than a simple timeline would suggest. The universe may have learned some of its tricks early. When Webb studies a deep field, it is not looking at one galaxy in isolation. It is looking into a crowded history where every object belongs to a larger structure. In its first deep field, centered on the galaxy cluster SMACS 0723, the foreground cluster appeared as it was about 4.6 billion years ago. Behind it, fainter and older galaxies were magnified and distorted by the cluster's gravity. This is gravitational lensing, mass bending the path of light. The cluster becomes part of the instrument. Nature adds a lens to the telescope. That image covered a tiny patch of sky, often compared to a grain of sand held at arm's length. Yet inside that tiny patch were thousands of galaxies. The comparison is useful because it turns abstraction into unease. Hold a grain of sand up to the sky, imagine the area it hides, and then imagine that within such a small window there are not stars, but galaxies, each with billions of stars of its own. The lesson is not only that the universe is large, the lesson is that deep time is densely packed. Even a keyhole can open onto an archive, and each galaxy in that archive is caught at a different stage. One may be a mature cluster member from billions of years ago, another may be a stretched background system from much earlier, another may be distorted into an arc because its light has been pulled around gravity, another may be faint enough that its identity depends on careful measurements through many filters. In an ordinary photograph, objects share the same moment. In a Webb deep field, they share the same arrival. It is a now built from delays, a now assembled from ancient departures, a now in which the universe does not appear as a single age, but as overlapping evidence. The old light does not arrive wearing a label that says what it means. Scientists have to earn the meaning through measurement, models, comparison, and caution. But once the measurements begin to settle, a pattern emerges. The distant universe was not empty waiting for galaxies. It was already busy, already forming, already colliding, already enriching itself. And this is where the title becomes more than a dramatic phrase. Webb captured evidence of cosmic evolution because it captured galaxies at different distances, different redshifts, different shapes, different chemical states, and different rates of star formation. It captured star birth nearby and galaxy assembly far away. It captured ancient light that still reaches us as a real physical signal. It captured the universe not as a finished object, but as a chain of becoming. The chain begins with gravity, but it does not end there. Gravity can gather the material, but gas must cool before it can collapse. If gas remains too hot, its particles move too quickly and resist falling into dense stars. If gas can radiate energy away, it can settle, fragment, and form stellar nurseries. Cooling depends on composition. Pure hydrogen and helium can cool in limited ways, but heavier elements and dust create new pathways for energy to escape. That means the first generations of stars change the conditions for the generations after them. A first generation of stars does not merely light the darkness, it changes what future darkness can do. Before those first stars, the universe was chemically simple. Hydrogen and helium dominated. There were no rocky planets, no dust-rich clouds like the ones Webb sees in nearby star nurseries, no carbon chemistry waiting quietly in cold gas. Then stars began to work. In their cores, fusion built heavier elements step by step, turning light nuclei into more complex ones under pressure and heat. When the most massive stars died, they scattered that new material outward. Their deaths became instructions for the next wave of creation. That is why a galaxy's light is not only brightness, it is history. When Webb detects signs of oxygen or carbon in a distant galaxy, it is not simply checking a chemical box. It is seeing evidence that stars had already lived and died there before the light began its journey. The galaxy was not at the first page. It had already passed through earlier cycles of birth, burning, death, and recycling. Cosmic evolution had already become layered. This is one of the reasons the earliest Webb galaxies feel so important. If a galaxy less than 1 billion years after the Big Bang already shows strong star formation, significant mass, dust, or chemical enrichment, then its story must have begun even earlier. The light reaching us is not the start of the process. It is the visible part of a chain that had been running before the image was made. A young galaxy can carry evidence of an even younger past. The timescales are difficult to hold. 1 billion years sounds enormous beside a human life, but beside a 13.8 billion year universe, it is early morning. If the entire age of the universe were compressed into a single year, the first billion years would fit into January. Human civilization would arrive in the final seconds of December 31st. In that compressed calendar, Webb is finding galaxies already active near the beginning of January, already building stars, already changing their gas, already preparing the material for later cosmic chapters. This does not mean the old models were worthless. The basic framework still matters. Gravity grows structure from small early fluctuations. Dark matter helps organize where gas can collect. Gas cools and forms stars. Stars alter the gas, and galaxies grow through both internal star formation and external merging. But Webb has sharpened the question. Not whether galaxies formed. They did. Not whether they evolved. They must have. The question is how fast, how efficiently, and under what conditions the universe built them. To answer that, Webb does not only look for the most distant objects, it also surveys large areas of sky, because cosmic evolution cannot be understood from a few spectacular extremes alone. One strange galaxy can mislead. A large population can reveal a pattern. This is why surveys like Cosmos Webb matter. By examining hundreds of thousands of galaxies across multiple wavelengths, astronomers can compare shape, brightness, color, estimated distance, stellar mass, dust, and star formation across cosmic time. The goal is not just to find record breakers. The goal is to see how the whole population changes. Population is important because evolution is never only individual. A galaxy is not born into emptiness. It lives in an environment. Around it stretches the cosmic web, the vast network of filaments and nodes formed as gravity amplified tiny density differences from the early universe. Matter did not collect evenly. It gathered along threads, intersections, and dense regions where galaxies could grow faster, collide more often, and feed from shared reservoirs of gas. If galaxies are cities of stars, the cosmic web is the landscape of roads, rivers, and crowded crossroads that decide which cities rise quickly and which remain small. This environmental story matters because it turns cosmic evolution from a simple age sequence into a geography of fate. Two galaxies at the same cosmic time may not live the same life. One may sit in a dense region where mergers and fresh gas drive rapid growth. Another may form in a quieter place, building more slowly. A third may fall into a cluster where its gas is stripped, heated, or exhausted. Time matters, but location matters too. The universe does not evolve like a single organism. It evolves like weather across an enormous terrain. That is why Webb's ability to measure galaxy shape is so valuable. Shape is memory. A smooth disk suggests a system where stars and gas have settled into rotation. A disturbed shape may suggest a merger, tidal interaction, or violent instability. A compact dense core may hint at rapid early assembly. A stretched arc may be a background galaxy bent by gravity. A clumpy young system may be forming stars in uneven bursts. None of these features tells the whole story alone. But together they become a language. And Webb reads this language with infrared clarity. Older telescopes, especially Hubble, transformed our understanding of deep time, but Hubble was not optimized for the longest infrared wavelengths Webb can observe. For the most distant galaxies, this matters because their light has been stretched so far that what began as ultraviolet emission from hot young stars may arrive as infrared. Without that infrared sensitivity, the earliest chapters remain dim or invisible. Webb does not replace Hubble. It extends the conversation into wavelengths where the ancient universe has been waiting. The result is not just more detail, it is a different kind of evidence. A distant galaxy's shape, its color, its spectrum, its brightness at several wavelengths, and its position among other galaxies all begin to answer one central question. What stage of becoming are we seeing? Is this a young system still gathering itself? Is it a starburst burning through fuel? Is it a merger assembling something larger? Is it already chemically enriched? Is it beginning to quiet down? Each answer is a point on the evolutionary map. But the map is not simple, because evolution is not always growth. This is the first major intuition break after the opening. We tend to imagine the young universe as a place of building, gas gathering, stars igniting, galaxies growing. That is true, but incomplete. To evolve is also to lose. A galaxy can run out of cold gas. It can heat its gas until it no longer collapses easily. It can blow material outward through stellar winds, supernovae, or black hole activity. It can enter an environment that strips away its fuel. The same universe that makes galaxies also finds ways to starve them. A living body needs food and oxygen. A galaxy needs cold gas. The comparison is not exact, but it is useful. Stars are not made from intention or beauty. They are made from material. Remove the material, heat it, scatter it, or prevent it from cooling, and the galaxy may keep shining with old stars while losing the ability to make new ones. From far away, it may still look magnificent. Internally, its future has changed. This is where the evidence becomes quietly unsettling. Webb is not only finding signs of early construction, it is helping reveal that the processes capable of slowing or ending star formation may also have appeared surprisingly early. Outflows, feedback, mergers, and compact intense star formation are not late decorations on a mature universe. They may be part of the early engine itself. The universe was not simply learning how to build galaxies, it was already learning how to regulate them, damage them, and sometimes shut them down. But to understand how a galaxy can begin to starve, we first have to make the fuel feel real. Cold gas is not background scenery. It is the reserve from which future stars are made. In many galaxies, especially young ones, that gas is uneven, turbulent, and constantly being pushed around by gravity, radiation, rotation, and explosions. A cloud may begin to collapse in one region, while another part is blasted apart. A galaxy is not a calm bowl of stars. It is a weather system made of matter, heat, and motion. When stars form rapidly, they do not form gently. Massive young stars pour out ultraviolet radiation. Their winds push into surrounding gas. After only a few million years, the most massive among them explode as supernovae, driving shock waves through the galaxy. Each explosion releases enough energy to disturb enormous volumes of gas. One supernova alone cannot control a galaxy, but many clustered together can create a pressure front, carving cavities, lifting material, and sometimes helping launch a galactic wind. That wind is not like air moving across your face. In space, it can be a vast outflow of gas driven by accumulated energy, radiation pressure, and sometimes the activity of a central black hole. If enough material is pushed away from the dense regions where stars would normally form, the galaxy's future changes. It may still shine with the stars it already made, but its next generation becomes harder to build. The light remains, the growth slows. This is the hidden severity inside the word feedback. Feedback sounds technical and mild, but in galaxy evolution it means that star formation can regulate itself. The birth of stars can create conditions that make later star birth more difficult. A galaxy can become too successful too quickly, burning and blasting through the material it needs to continue. It is a cosmic version of a fire consuming its own fuel while throwing sparks into the room around it. Webb's contribution is to make this kind of story harder to ignore at high redshift, where the universe was young and galaxies were expected to be rapidly forming stars. If an early galaxy already shows evidence of powerful outflows, then the young universe was not just assembling stellar systems, it was also beginning the long struggle between growth and self-limitation. That struggle is one of the main engines of cosmic evolution. Without it, galaxies would not have the sizes, shapes, colors, and life histories we observe today. Imagine a galaxy in the first billion years after the Big Bang, not as a peaceful island, but as a compact furnace. Gas pours inward, stars ignite in crowded regions, massive stars die quickly, energy floods the surrounding medium, gravity keeps trying to gather more material, while radiation and explosions keep trying to rearrange it. The galaxy is young, but youth does not mean simplicity, it means intensity. This is why a single number, when translated properly, can feel so dramatic. If a galaxy is losing gas at hundreds of solar masses per year, that does not mean a gentle leak. One solar mass is roughly the mass of our Sun. Hundreds of solar masses per year means the raw material equivalent of hundreds of suns being driven outward annually. Over 10 million years, a short interval for a galaxy, That becomes billions of solar masses of material removed, heated, or displaced. The number is not just large, it is a future being carried away. And if the outflow rate is comparable to, or greater than, the rate at which new stars are forming, the balance becomes crucial. Star formation is no longer only a sign of vitality. It may also be a warning that the system is under stress. The same burst that makes the galaxy bright can help drain the reservoir that would have made it brighter in the future. Growth and decline can begin in the same fire. That is the midpoint turn of the whole journey. At first, cosmic evolution sounds like a story of emergence. Gas becomes stars. Stars become galaxies. Galaxies become structure. Structure becomes the universe we see now. But Webb is helping us see that evolution also includes interruption. It includes fuel loss, heating, violence, exhaustion, and environmental pressure. The universe was not only learning how to make galaxies, it was already learning how to end their star-making lives. This does not make the story darker in a cheap way. It makes it more real. Nothing in nature evolves by simply adding more and more complexity forever. Systems grow under constraints. A forest depends on rain, soil, sunlight, fire, and competition. A body depends on circulation, repair, energy, and balance. A galaxy depends on gas supply, gravity, cooling, feedback, and environment. Remove one part of the balance, and the visible beauty may remain for a while, but the underlying process changes. A galaxy that stops forming stars does not vanish. It can keep shining for billions of years with older stellar populations. To an untrained eye, it may still appear grand and complete, but its color, spectrum, gas content, and star formation rate tell a different story. Young blue stars are short-lived, so if new ones are no longer forming, the blue light fades. Older, redder stars dominate. The galaxy becomes quieter, not because its stars have disappeared, but because its future has thinned. This is one of the most important distinctions Webb helps bring into focus. Appearance is not evolution by itself. A bright galaxy may be young and growing, or it may be briefly bright because of an intense burst that cannot last. A red galaxy may be ancient and passive, or it may be dusty and actively forming stars hidden from visible view. A compact galaxy may be a young seed, or the dense core of something that formed rapidly. To understand the stage, astronomers need more than a photograph. They need light measured carefully enough to reveal temperature, dust, redshift, composition, and motion. Spectroscopy is where the image becomes interrogation. Webb can split a galaxy's light into its separate wavelengths, and those wavelengths act like fingerprints. Emission lines can show gas excited by young stars or active black holes. Absorption features can hint at older stellar populations. The position of these lines reveals redshift. Their strength can suggest chemical abundance, ionization, dust, and star formation conditions. A spectrum is not glamorous in the same way as a deep field image, but scientifically it can be more intimate. It asks the galaxy what happened inside it, and the answer is rarely one thing. A distant galaxy may carry the light of millions or billions of stars blended together into a single faint signal. It may contain dust hiding part of its activity. It may be magnified by gravitational lensing. It may be interacting with a neighbor. It may host a feeding black hole whose glow contaminates the light from stars. Scientists must separate possibilities without pretending the uncertainty is gone. This is not weakness. This is how real knowledge is built. That is why the most honest picture of Webb's discovery is not a clean headline, but a careful ladder. First, the telescope receives photons. Then instruments measure where those photons fall in wavelength. Then astronomers compare the pattern with known physics: hydrogen, oxygen, carbon, dust, stellar populations, black hole activity, and the expected effects of cosmic expansion. Only after that can a distant smudge become a galaxy at a certain redshift, with a certain likely mass, forming stars at a certain rate, perhaps losing gas, perhaps merging, perhaps entering a new stage of its life. The process is slow, but that slowness makes the evidence trustworthy. The universe does not explain itself in captions. It arrives as light, and light must be translated without forcing it to say more than it can. Webb has made the translation richer because it sees wavelengths older telescopes could not see as clearly. especially in the infrared where early galaxy light has been stretched. But even Webb is not magic. Its greatness comes from how precisely it lets us ask the old questions. One of those old questions is simple enough for a child to ask and difficult enough to occupy generations of scientists. How did galaxies become what they are? Look at the Milky Way today, and it seems almost settled. A broad disk of stars, spiral arms, dust lanes, a central bulge, a halo of older stars and dark matter. Around 100,000 light-years of structure, motion, memory, and invisible gravity. It feels like a place. But the Milky Way was not born as the Milky Way. It assembled. Smaller systems merged into it. Gas fell in. Stars formed across different eras. Some stellar populations are old enough to remember an earlier galaxy. Others, like the Sun, formed later from gas already enriched by stellar death. Even now, our galaxy is not finished. It is moving toward a future interaction with Andromeda, and it still contains star-forming regions where new suns are being made. A galaxy is not a statue. It is an event that lasts for billions of years. Webb's deep observations help us place that event inside a larger family history. If we see galaxies at high redshift that are compact and intensely star-forming, we may be looking at distant relatives of the building blocks from which larger galaxies grew. If we see disturbed shapes, we may be seeing collisions and mergers in progress. If we see early disks, we may be seeing rotation and structure settling sooner than expected. If we see quiescent galaxies, systems with little star formation, we may be seeing evidence that some galaxies reached maturity and began shutting down surprisingly early. This is where cosmic evolution becomes more than a timeline. It becomes competing forces. Gravity builds. Cooling allows gas to collapse. Rotation spreads material into disks. Turbulence breaks smoothness into clumps. Mergers disturb order and can trigger starbursts. Feedback pushes back. Black holes may heat or expel gas. Environment can feed a galaxy or strip it. Over time, these forces do not simply add up, they interact, sometimes reinforcing one another, sometimes changing the direction of the whole system. A galaxy merger is a good example because it looks like destruction and construction at once. Two galaxies approach under gravity, but they do not collide like solid objects. Stars are so far apart that most pass by without hitting. The drama is in the gas. Gas clouds can be compressed, shocked, and driven inward. That inflow can ignite new star formation or feed the central black holes. Tidal forces stretch arms and tails across space. The shape becomes disturbed. But the disturbance may help build something larger. The wreckage is also architecture. This is why Webb's sharp infrared images matter for distant mergers. In the early universe, galaxies are small, faint, and often dusty. A feature that looks smooth in a weaker image may become clumpy with better resolution. A single object may turn out to be multiple components. A red point may hide an active nucleus, heavy dust, or an older stellar population. Webb lets astronomers separate these possibilities with more care. It does not remove ambiguity from every case, but it thins the fog. And once the fog thins, the universe looks less orderly than textbook diagrams sometimes suggest. There is no single road from primitive galaxy to modern spiral. There are many roads. Some galaxies grow through steady gas inflow. Some grow through violent mergers. Some flare with intense star formation and then fade. Some live in dense regions where encounters are common. Some remain isolated for long stretches of cosmic time. Some become compact and massive early, like they have compressed several chapters of life into a short cosmic morning. That is one reason Webb's early results have felt so electric. A compact massive galaxy in the young universe is not merely an object with impressive numbers. It is a challenge to timing. To become massive early, it must have converted gas into stars efficiently, formed in an unusually dense region, experienced intense mergers, or be interpreted cautiously because dust, black holes, or uncertainty can mimic some signs of mass. The excitement is not that one explanation wins instantly, but that the evidence forces better questions. Real science often advances this way, not through one spectacular image that settles everything, but through a pressure building across many observations. A few distant galaxies appear brighter than expected. Spectra confirm some distances and revise others. Surveys expand the sample. Models adjust star formation efficiency, feedback strength, dust behavior, or black hole contribution. The story becomes less like overthrow and more like sharpening a lens. The universe has not changed. Our ability to see its early work has improved. That improvement matters because the early universe is where small differences become enormous consequences. Tiny fluctuations in density, imprinted in the young cosmos, became the seeds of large-scale structure. Dark matter gathered first into gravitational wells. Gas fell into those wells. Where the wells were deeper, growth could accelerate. Where gas cooled efficiently, stars could ignite. Where stars formed, radiation and explosions changed the gas. Each step altered the next. Cosmic evolution is a chain where the result of one era becomes the starting condition of the next. This is why Webb's evidence feels almost intimate. Despite the distance, it is showing us the ancestry of conditions we live inside. The oxygen you breathe was not part of the universe's first simple inventory. The iron in your blood was not waiting at the Big Bang. The silicon beneath your feet, the carbon in your cells, the calcium in your bones, all belong to a universe that processed itself through stars. When Webb observes early chemical enrichment, it is not merely studying distant galaxies, it is studying the early steps of a recipe that eventually made worlds like ours chemically possible. But the recipe was never guaranteed to produce Earth. Most galaxies did not produce a human planet. Most stars did not become the sun. Most planets did not become living worlds. Cosmic evolution is not a straight road leading to us. That would be too small. The larger truth is that we are one rare consequence inside a much broader set of processes. Gravity gathering matter, stars making elements, galaxies recycling gas, planets forming from enriched dust, and life emerging under conditions that could easily have been otherwise. Webb makes that broader story visible without needing to flatter us. It does not show a universe designed around human beings. It shows a universe active enough, old enough, and chemically creative enough that beings like us could appear somewhere inside it and look back. That is more honest wonder. We are not the center of the picture. We are the late evidence that the picture became complicated. And because we are late evidence, every ancient galaxy Webb finds carries a double meaning. It belongs to its own time, its own environment, its own physical struggle. But it also belongs to the long explanation of why our universe is not chemically silent. A faint red galaxy is not just a distant object. It is part of the chain that transformed simple matter into stars, dust, planets, atmospheres, and eventually observers. To follow that chain, we have to look not only at bright galaxies, but at the spaces between them. The universe on the larger scales is not sprinkled randomly with galaxies like salt on black cloth. It has structure. Galaxies gather along filaments, walls, and intersections, leaving vast regions comparatively empty. This cosmic web is one of the most important clues to how evolution works, because it shows that gravity has been organizing matter from the beginning. The web is not decoration around galaxies, it is the landscape in which their lives unfold. The seeds of that web were tiny. In the early universe, matter was almost evenly distributed, but not perfectly. Some regions were slightly denser than others. Gravity made those regions grow denser over time, pulling in more matter, deepening their own attraction. Dark matter, which does not shine but does exert gravity, played a central role in building the invisible scaffolding. Ordinary gas fell into those dark matter structures, and where conditions allowed, stars and galaxies followed. This means a galaxy's destiny begins before it becomes visible. Long before its stars shine brightly enough for Webb to see, the gravitational environment has already shaped what kind of growth is possible. A shallow dark matter halo may struggle to hold gas after stellar explosions. A deeper one may gather and retain more material. A dense intersection of filaments may feed rapid assembly. A crowded region may produce frequent mergers. The light Webb sees is the visible surface of an older invisible architecture. That architecture matters because it helps explain why early galaxies can surprise us. If some regions of the young universe were unusually dense, galaxies there could grow faster than average. They could pull in gas more efficiently, they could merge more often, they could build stars in intense bursts. So when Webb finds a galaxy that appears too bright, too massive, or too chemically advanced for a simple expectation, One possibility is not that physics failed, but that the galaxy formed in an exceptional neighborhood. Cosmic evolution has local weather. A human analogy helps, as long as we do not push it too far. Two children born in the same year may grow up under very different conditions. One may have abundant food, safety, and support. Another may face scarcity and stress. Their age is the same, but their development is not. Galaxies are not people, yet the principle of environment still matters. Cosmic age tells us when the light left. It does not tell us everything about the conditions that shaped the object before that light began its journey. This is why large surveys are so important. A single unusual galaxy can make a dramatic headline, but it cannot define the universe alone. To understand evolution, astronomers need populations, many galaxies, over wide areas, with measured colors, shapes, redshifts, masses, and star-forming behavior. They need to know what is common, what is rare, what changes smoothly with time, and what appears only in special environments. Webb's deepest value is not only in its most spectacular images. It is in the statistical weight of many faint things measured carefully. A survey turns the sky into a census of time. Nearby galaxies offer later stages. More distant galaxies offer earlier stages. Very distant galaxies approach the first chapters we can observe. By comparing them, scientists can reconstruct how the average galaxy population changed, how star formation rose and fell across cosmic history, how disks became common, how massive galaxies assembled, how black holes and feedback altered growth, and how some galaxies became quiet while others continued forming stars. One of the great discoveries of modern astronomy, even before Webb, is that the universe did not form stars at a constant rate forever. Star formation rose during the early billions of years, reached a broad peak roughly 10 billion years ago, and then declined toward the present day. The universe today still makes stars, including inside the Milky Way, but it is quieter than it once was. We live in a cosmos after its brightest age of starbirth. The fire has not gone out, but it has lowered. Webb helps fill in the earlier side of that curve, the part where the first galaxies began turning gas into stars. This is a difficult region to study because the objects are faint, redshifted, and often small, but it is crucial because the slope of that early rise tells us how quickly the universe moved from darkness into structure. A small change in early star formation can alter when galaxies become enriched, when black holes begin feeding, when radiation changes surrounding gas, and when later populations can emerge. The phrase cosmic dawn is often used for this era, and it is easy for that phrase to become sentimental. But the real dawn was physical. The first luminous sources produced ultraviolet radiation that began changing the surrounding hydrogen gas. Over time, that radiation contributed to a process called reionization, when much of the neutral hydrogen between galaxies became ionized again. This was not a sunrise over a landscape. It was a transformation in the state of intergalactic matter. Light did not simply appear, it changed what space between galaxies was like. Webb's earliest galaxies are tied to that transformation. If small young galaxies produced enough energetic light that escaped into the surrounding universe, they may have helped drive reionization. But escape is not automatic. Radiation can be absorbed by gas and dust inside the galaxy. The shape of the galaxy, the burstiness of star formation, and feedback from stars may open channels through which radiation leaks out. Again, mechanism matters. It is not enough to say early galaxies lit the universe. We need to know how their light escaped. Here the image becomes almost tactile. Imagine a young galaxy as a stormy, clumpy system filled with gas. Stars ignite in dense regions. Massive stars push and ionize their surroundings. Supernovae punch cavities through the gas. Some pathways clear enough for radiation to stream outward into intergalactic space. Others remain blocked. The galaxy is not a lamp with a clean glass cover. It is more like a burning building with smoke, holes, pressure, and broken walls, where light escapes unevenly through gaps created by its own violence. That unevenness may be part of why early galaxies look so varied. Some shine brightly in certain wavelengths because young hot stars dominate. Some are reddened by dust. Some appear compact and intense. Some may hide active black holes. Some may be magnified by lensing, making them easier to study than they otherwise would be. Each case requires caution, but together they show a young universe that was already complex enough to resist a simple picture. This is where Webb's evidence begins to feel like real-time evolution in the only honest cosmic sense. The telescope is catching active processes at many stages: stars forming inside dust nearby, galaxies blazing with young stars far away, ancient systems showing enrichment, winds carrying gas out, mergers disturbing shapes, and large-scale structure guiding where growth happens. These are not artists' impressions of change. They are signals from matter in the act of changing, delayed by distance, arriving in our present. The delay does not make them less real. It makes them more astonishing. When you look at a distant galaxy, you're not seeing what it is doing today in its own local present. You're seeing what it was doing when the light left. That galaxy may have changed beyond recognition by now. It may have merged, quieted, grown, or vanished into a larger system. But the light that left during that ancient phase is real. It preserves the state of the process at that moment. The universe lets us see its past, not because the past remains nearby, but because the past is still arriving. The past is still arriving, and Webb was built to notice the faintest parts of its arrival. That single idea changes the meaning of almost every deep space image. A galaxy is not merely located at a distance, it is located at a delay. Its light has spent billions of years crossing an expanding universe, being stretched, dimmed, and sometimes bent before reaching a mirror parked far beyond Earth's atmosphere. By the time Webb collects it, the galaxy has already become something else. But the signal remains faithful to the moment it left. This is why astronomers speak carefully about look-back time. If a galaxy's light has travelled for more than 12 billion years, then the telescope is seeing that galaxy as it was more than 12 billion years ago. But the galaxy itself, if it still exists in some descendant form, has had all that time to keep evolving. We do not see its current state, we see one preserved layer of its history. The sky is full of these layers, and Webb is sensitive enough to separate more of them than ever before. Still, separating layers is not the same as understanding them. The universe does not arrange its evidence for our convenience. A very distant galaxy can appear faint because it is small, or because it is dusty, or because it is far, or because some of its light has been absorbed by gas between galaxies. A galaxy can appear bright because it is forming stars rapidly, or because a black hole is feeding at its center, or because gravitational lensing has magnified it, or because several objects are blended together. The first act of good astronomy is not excitement, it is suspicion. This suspicion is one of the reasons Webb's discoveries are so valuable. They do not merely add more pictures, they force every interpretation to pass through better data. A candidate galaxy may first be identified through imaging, where its brightness in different filters suggests a high redshift. Then spectroscopy, if possible, can confirm the distance by detecting shifted spectral features. If spectroscopy is not available, astronomers compare models, uncertainties, and alternative explanations. Some candidates survive, some move closer, some turn out to be less distant than first thought. The story improves because the mistakes are found. That may sound less dramatic than a headline, but it is far more powerful. Science becomes trustworthy when it can correct itself without losing its desire to know. Webb has produced early surprises, but the honest lesson is not that everything before it was wrong. The lesson is that the early universe had more texture than our older instruments could fully resolve. When a dim blur becomes a structured galaxy, when a red point becomes a spectrum, when a statistical sample replaces a handful of record-breaking objects, reality becomes less vague. And in that sharper reality, one pattern keeps returning. The young universe was active. It was not waiting quietly for billions of years before becoming interesting. Within the first billion years, galaxies were already forming stars, enriching gas, gathering mass, and shaping their surroundings. Some were small and faint, some were unexpectedly luminous, some were likely caught during intense bursts of star formation. Some may have contained early black holes. Some appear disturbed, compact, or clumpy, as if still negotiating their own structure. Clumpiness matters because it reveals instability. In a young gas-rich galaxy, star formation may not be smoothly spread like a gentle glow. It may ignite in giant knots where gas collapses rapidly. Those knots can dominate the light, making the galaxy look irregular or fragmented. Over time, rotation, feedback, mergers, and gas inflow can rearrange the system. A disk may settle, a central region may grow, a burst may fade. The shape is not cosmetic. It is evidence of how matter is moving. When Webb sees such shapes at high redshift, it asks whether the universe built ordered structures earlier than expected, or whether what looks ordered is still temporary and turbulent. A disk, for example, is not just a pretty spiral. It requires angular momentum, gas settling, and a system that has not been completely disrupted by recent violence. If disks appear very early, models must explain how gas cooled, rotated, and stabilized so quickly. If many early systems are instead disturbed, that supports a picture of rapid assembly through mergers and clumpy star formation. The point is not to force one answer. The point is that morphology becomes evidence. Morphology also connects cosmic evolution to the eventual variety of galaxies we see nearby. In the local universe, galaxies are not all the same. Some are blue spirals with active star formation. Some are red elliptical systems dominated by older stars. Some are irregular, stretched, or interacting. This variety is not random. It reflects different histories of gas supply, mergers, feedback, environment, and time. Webb lets us search for the earlier stages of that variety. It asks when the Great Division began between galaxies that keep making stars and galaxies that grow quiet. That division may be one of the most important features of the universe we live in. A star-forming galaxy is chemically and visually alive in a particular way. It continues creating short-lived blue stars. It refreshes its stellar population. It may build new planetary systems. A quenched galaxy is not dead, but it is no longer renewing itself in the same way. Its older stars can shine for ages, but the bright blue signal of new formation fades. The galaxy becomes more like a memory palace, full of light, but less full of beginnings. How does a galaxy cross that boundary? There is no single answer. It might exhaust its cold gas by turning much of it into stars. It might lose gas through winds driven by supernovae or black hole activity. Its gas might be heated so it cannot cool and collapse efficiently. It might fall into a cluster where interactions strip gas away. Its central black hole may inject energy into surrounding material, preventing future star formation. The mechanisms vary, but the result is similar. The reservoir for new stars becomes unavailable. This is why cosmic evolution has to be understood as a balance between supply and resistance. Gas flows in, gravity compresses it, cooling allows collapse, stars form. Those stars produce energy that heats and disrupts the gas. Some gas escapes, some remains, some falls back later. A black hole may feed and send energy outward. A merger may both deliver new gas and disturb the existing structure. Each galaxy is a negotiation, and the outcome depends on which processes dominate at which time. Webb's great strength is that it catches many negotiations at once. It does not watch one galaxy for 1 billion years, but it can compare galaxies whose light left at different ages of the universe. That comparison becomes a kind of reconstructed motion. If distant early galaxies are smaller, more irregular, and more star-forming, while later populations show more settled structures and more quenched systems, then the evolutionary sequence begins to appear, not as a simple cartoon, but as a population-level transformation. This is the hidden meaning of real time at cosmic scale. We cannot wait long enough to watch one massive galaxy live its whole life, but we can look across distance and gather many galaxies at different life stages. It is like entering a forest where seedlings, young trees, mature trunks, fallen branches, and decaying wood all exist at once. You do not need to watch one tree for centuries to understand that a forest changes. The evidence is distributed across the living scene. The universe gives us a forest made of time. Nearby galaxies are later growth. Distant galaxies are earlier growth. Star-forming clouds show the local mechanism of new light being made. Ancient redshifted galaxies show those mechanisms operating when the cosmos was young. Quenched systems show that star formation can fade. Mergers show that structure can be rebuilt through disturbance. The cosmic web shows that environment shapes the whole forest. Webb is not watching one tree grow. It is revealing that the forest was never still. And once you see that, the night sky becomes less like a ceiling and more like a process continuing beyond our reach. Every faint source is either forming, fading, colliding, feeding, exhausting, or carrying the residue of something that happened before. Even silence becomes active, because dark regions are not empty of meaning. They may be under dense voids, dust-obscured structures, or simply places where the light is too faint for us to catch. Absence can also be evidence. If you know what should have been there, that is the deeper change Webb brings. It does not only add objects to the cosmic inventory, it changes how we imagine change itself. Evolution is no longer something reserved for life on Earth or fossils in rock. It is written into the behavior of matter under gravity, radiation, pressure, cooling, chemistry, and time. The universe evolves because matter responds to conditions, and those responses become new conditions for what follows. Each generation of stars alters the next. Each merger rewrites structure, each outflow changes the future supply of fuel. And somewhere inside that chain, long after the earliest galaxies began their work, our own ordinary-looking world became possible. Our own ordinary-looking world became possible because the universe had already spent billions of years changing its raw material. Earth is not made from the first simple gas. It is made from the aftermath of stars. The rock under your feet, the oxygen in the air, the iron in your blood, the calcium in your bones. All of it belongs to a universe that had to evolve chemically before a planet like this could exist. Webb's distant galaxies are not directly our ancestors in a simple line, but they belong to the same family of processes that made ancestry possible at all. This is why cosmic evolution is more intimate than it first appears. It sounds like something happening far away, among galaxies too faint to see without a machine the size of a house, working in cold darkness a million miles from Earth. But the same physics that Webb studies in ancient galaxies is written into local existence. Gas collapses, stars ignite, elements form, dust gathers, planets assemble, chemistry becomes richer. Some worlds remain sterile. One world, at least, becomes aware enough to ask where its atoms came from. The answer is not a single place, it is a history. That history includes the Milky Way itself, which is often treated as our stable home but is really another evolving system. Our galaxy contains old halo stars that formed long before the Sun, a thin disk where younger stars continue to appear, thick disk populations carrying the memory of earlier heating and mergers, and satellite galaxies being pulled apart by gravity. Streams of stars around the Milky Way are like torn pages from smaller galaxies that fell in long ago. Even home is assembled from events. The Sun formed about 4.6 billion years ago, from a cloud already enriched by earlier generations of stars. By then, the universe was more than 9 billion years old. That means the solar system belongs to a late chapter, not an opening scene. The atoms that built Earth had passed through earlier cycles of stellar birth and death before they became part of the dust and gas that formed our planetary system. In a very real sense, we live inside cosmic after-effects. Webb looks backward from this late chapter. It searches for the earlier ones, not to find a direct photograph of our own beginning, but to understand the general conditions under which galaxies, stars, and elements became common enough for worlds to follow. Every early galaxy with signs of heavy elements tells us that enrichment had already begun. Every dusty starburst tells us that the raw universe had become chemically textured. Every compact luminous galaxy tells us that matter could organize quickly under the right conditions. Every quenched system tells us that growth could fail or pause. Failure is part of the story because evolution is not progress in a straight line. This is easy to forget. The word evolution often carries a false emotional direction, as if everything is always improving, becoming more complex, moving towards some final purpose. In the cosmos, evolution simply means change through physical processes. A galaxy can evolve by growing. It can evolve by being torn apart. It can evolve by losing gas. It can evolve by becoming quiet. It can evolve into beauty, or into exhaustion, or into something that later merges and disappears as a separate object. This makes Webb's evidence more honest. It shows no promise that the universe protects its creations. Young stars can destroy the clouds that made them. Supernovae can enrich space while sterilizing nearby worlds. Mergers can build larger galaxies while erasing smaller identities. Black holes can illuminate their surroundings while heating gas that might otherwise form stars. Cosmic evolution is not gentle, but Webb reveals it with a kind of calm, because the timescales are so vast that even violence becomes slow from our perspective. A galaxy collision, for example, may sound instant because the word collision belongs to human experience. We imagine impact, shattering, noise. But two galaxies passing through each other unfold over hundreds of millions of years. Stars usually do not smash into one another because the spaces between them are immense. The gas, however, responds. It compresses, shocks, loses energy, falls inward, and may form stars in bursts. Gravity stretches tidal tails across space like pale ribbons. What looks like catastrophe in a still image is really a long rearrangement of orbits, gas, and future light. Webb can make these rearrangements visible at distances where older instruments struggle to resolve the details. A pair of early galaxies may appear as separate knots embedded in a larger disturbed system. A compact source may show an extended halo when observed more deeply. A suspected single galaxy may split into components. These details matter because they tell us whether we are seeing isolated growth or assembly through interaction. The difference changes the evolutionary explanation. If galaxies mostly grew by calmly drawing in gas, their shapes and star formation would follow one kind of history. If mergers were frequent and important, then disturbance, burstiness, and rapid structural change become central. In reality, both matter. Gas inflow feeds galaxies. Mergers rearrange them. Feedback regulates them. Environment guides them. The universe is too rich for a single mechanism to explain every path. Webb's role is not to choose simplicity. It is to reveal where simplicity fails. That failure of simplicity is one of the great rewards of modern astronomy. The first rough map says galaxies grow over time. The better map says they grow differently depending on mass, gas, environment, feedback, and chance. The first rough map says early galaxies should be small. The better map asks which early galaxies, in which regions, under what conditions, with how much dust, how much black hole activity, and what kind of star formation. Science deepens when adjectives become mechanisms, and mechanisms become clearest when we ask what would happen if one part changed. If gas cannot cool, stars do not form efficiently. If feedback is too weak, galaxies may become too massive too quickly compared with what we observe nearby. If feedback is too strong, galaxies may fail to build enough stars. If black holes grow early, their radiation may alter the light we attribute to stars. If dust forms quickly, some galaxies may appear red or dim in ways that mimic age or distance. Every interpretation has a pressure point. This is why Webb's evidence must be joined with other observations, simulations, and theory. A telescope provides measurements, not complete understanding by itself. Models try to reproduce the universe from initial conditions, gravity, gas physics, star formation, feedback, chemical enrichment, and dark matter. When Webb finds galaxies that are brighter or more mature than expected, modelers do not simply throw away the universe. They adjust assumptions, test alternatives, compare populations, and ask which physical ingredients were underestimated. The most interesting outcome is not panic, it is refinement. Perhaps star formation was more efficient in some early halos. Perhaps feedback acted differently in compact young systems. Perhaps dust and black holes complicate the brightness. Perhaps lensing magnified some objects. Perhaps a few candidates are less distant than first thought. Or perhaps the early universe really did build certain structures faster than we had expected. Within the same broad laws, but through pathways we had not fully appreciated. That is the quiet power of Webb's view. It does not make reality theatrical. It makes reality more specific. It makes reality more specific, and specificity is where wonder becomes harder to dismiss. A vague claim can impress for a moment, but it does not stay. A clear mechanism stays. Once you understand that early galaxies may look unexpectedly bright because gas collapsed efficiently inside dense dark matter halos, or because a central black hole added light, or because a foreground cluster magnified them, the mystery becomes more durable. It is no longer a fog of amazement. It is a set of physical possibilities, each one testable, each one tied to something matter can actually do. This is why Webb's observations of distant galaxies often begin with color but cannot end there. Color tells us how the light has been distributed across wavelengths, but color alone can deceive. A galaxy may appear red because it is extremely distant and its light has been stretched. It may appear red because it contains older stars. It may appear red because dust absorbs shorter wavelengths and lets longer ones escape. 3 different histories can leave a similar first impression. Webb helps by observing through multiple filters and, when possible, by taking spectra that turn impression into a more disciplined question. The spectrum is like a confession, but only if we know how to listen. Hydrogen can leave marks, oxygen can leave marks, carbon can leave marks. Hot young stars can excite gas until it glows in certain lines. A feeding black hole can produce a harder, more energetic signature. Dust can tilt the light and hide what would otherwise be obvious. When those features appear, shifted toward longer wavelengths, astronomers can estimate how much the universe expanded while the light was traveling. Redshift becomes the ruler, the clock, and the first clue to the galaxy's place in cosmic history. But even a spectrum does not make interpretation effortless. It gives stronger constraints. It narrows the range of possible stories. That is how real evidence works. A galaxy at high redshift with strong emission lines may be forming stars intensely. But scientists still ask how much of the light comes from stars and how much might come from an active nucleus. A compact object with a surprisingly large inferred mass may be truly dense, or its mass estimate may shift when dust. Star formation history or black hole light is modeled differently. The careful answer is slower, but it is closer to reality. This carefulness matters because Webb has arrived at a moment when astronomy is trying to connect 2 kinds of truth. One is the truth of the individual object, this galaxy, this spectrum, this redshift, this shape. The other is the truth of the population, how galaxies as a whole changed across billions of years. A single extraordinary object can open a door. A population tells us whether the door leads to a rare room or an entire hidden wing of the universe. Large surveys give that population meaning. When astronomers examine hundreds of thousands of galaxies across a field, patterns emerge that no single image could prove. Massive galaxies become more common with time. Settled structures appear and evolve. Disturbed systems reveal the importance of mergers. Star-forming galaxies trace one history, quiescent galaxies another. The ratio between them changes as the universe ages. Webb's infrared reach adds earlier and fainter members to that census, pushing the evolutionary map closer to the beginning. And the beginning keeps resisting our desire for simplicity. The first galaxies did not all grow at the same pace. They did not all shine the same way. Some may have formed stars in short, violent bursts, then dimmed. Some may have sustained star formation longer. Some may have been fed by cold streams of gas flowing along filaments. Some may have been shaken by mergers. Some may have hosted early black holes whose light complicates the story. The young universe was not a single classroom of identical students. It was a crowded city of different lives beginning under different pressures. One pressure is gravity, the oldest architect in the room. Gravity does not need to hurry. It only needs time and slight imbalance. A region with a little more matter pulls more strongly, gathers more material, and deepens its own well. Gas falling into that well gains energy, heats, cools, and may settle into dense regions. Dark matter provides much of the gravitational scaffolding, while ordinary matter provides the light. The galaxy we see is the luminous response to an invisible structure. Another pressure is cooling. Gas cannot form stars efficiently if it cannot lose energy. Collapse converts gravitational energy into heat, and hot gas resists further collapse. To become a star, some portion of that gas must radiate energy away, become denser, and fragment. In a chemically young universe, cooling pathways were more limited. As stars created heavier elements and dust, later gas could cool in new ways. That means chemical enrichment was not just a byproduct of star formation. It changed the conditions for future star formation. The universe became better at making structure because earlier structure had already changed the rules. A third pressure is feedback. Stars do not passively sit inside galaxies after they form. The most massive stars blast radiation into their surroundings, drive winds, and end as supernovae. These processes can compress some gas while dispersing other gas. They can trigger formation in one region and suppress it in another, At galaxy scale, feedback prevents simple runaway growth. Without it, models often create galaxies that are too massive, too dense, or too efficient compared with what we observe. Feedback is the universe pushing back against its own construction. Then there is black hole feedback, deeper and more extreme. In the centers of many galaxies, supermassive black holes can grow by accreting gas. The gas falling inward heats and radiates before crossing the event horizon, sometimes producing enormous luminosity from a region smaller than the galaxy around it. Jets or radiation can inject energy into surrounding gas, heating it or driving it outward. This can reduce the gas available for star formation. A black hole is not simply a dark object at the center. In the right phase, it can become a regulator of a galaxy's future. These pressures make cosmic evolution feel less like a family tree and more like a climate system. There are trends, but there are also storms. There are average histories, but there are also exceptional places. Gravity gathers, cooling enables, stars ignite, feedback resists, black holes intervene, environment redirects. The final galaxy is not the result of one cause. It is the negotiated outcome of many causes acting over immense time. Webb's images matter because they allow us to see that negotiation earlier, not after everything has settled into familiar nearby forms, but while the arguments are still visible, clumps not yet smoothed, mergers not yet relaxed, bursts not yet faded, gas not yet fully consumed, structures not yet stable. The farther back Webb looks, the less the universe resembles a finished city, and the more it resembles scaffolding, furnaces, collisions, and half-built roads. Those half-built roads are difficult to recognize because the universe never labels them for us. A clumpy young galaxy does not announce whether it will become a spiral, merge into something larger, fade into quietness, or disappear as a separate system inside a greater halo. We see the light from one phase and must infer the possible paths. That uncertainty does not weaken the evidence. It makes the evidence alive, because evolution is always a record of paths taken and paths closed. This is where the idea of real time becomes almost philosophical, but still grounded in physics. We cannot watch one ancient galaxy make all its choices. Its clock does not run for us. But by observing many galaxies at many look-back times, we can place different phases beside one another. We can see active star formation in one population, disturbed mergers in another, compact early structures in another, and quiet older systems later in the record. It is not a movie frame by frame. It is more like finding thousands of pages from different chapters, then realizing the grammar of change is consistent across them. That grammar begins in gas and ends, sometimes in silence. Gas is the raw future of a galaxy. Stars are the visible present. Old stars are the memory. If a galaxy has plenty of cold gas, it can keep making new stars. If that gas is consumed, expelled, heated, or prevented from cooling, the galaxy's future narrows. This is why astronomers care so much about star formation rates. A galaxy forming one solar mass of stars per year is living at one pace. A galaxy forming tens or hundreds of solar masses per year is in a much more intense phase. But intensity is not always stability. A blaze can be temporary. The Milky Way today forms stars at only a modest rate, roughly a few solar masses per year under common estimates. It is not dead, but it is not in a wild starburst either. Compare that with young galaxies whose inferred star formation rates can be tens or even more than 100 solar masses per year, and you begin to feel the difference between a quiet adult system and a compact early furnace. If the Milky Way is a city with a few new neighborhoods being built each year, some early starburst galaxies are construction sites glowing through the night, using material at a pace that may not last. That pace matters because stars of different masses live very different lives. A small red dwarf can burn for hundreds of billions or even trillions of years, far longer than the current age of the universe. A massive blue star may live only a few million years before exploding. So a galaxy's bright blue light is often a sign of recent star formation, because those massive stars do not linger. If the birth of new massive stars stops, the blue signal fades quickly on cosmic timescales. The galaxy's color shifts, and with it, the evidence of its recent life. This is how light becomes a clock inside the galaxy itself, not just the travel time from galaxy to telescope, but the ages of the stars contributing to the light. Young stars leave one kind of signature, older stars leave another. Dust changes both. Gas emission adds another layer. A feeding black hole can confuse the reading. A galaxy is like a room where many conversations overlap, and Webb gives us a better microphone, not a guarantee that every voice is instantly separated. Still, the improvement is extraordinary. When Webb detects a distant galaxy in several infrared filters, astronomers can compare how bright it appears at each wavelength. That pattern, called its spectral energy distribution, can be matched with models of stellar populations, dust, redshift, and star formation. It is not as definitive as a clean spectrum, but for large surveys it becomes essential. It lets scientists estimate properties for huge numbers of galaxies, building the population-level story that no single target can provide. And population-level change is what cosmic evolution truly means. One galaxy may be strange, 10 galaxies may be suggestive, hundreds of thousands begin to reveal the shape of history. If disk-like structures appear earlier than expected, that says something about how quickly rotation and stability can emerge. If disturbed galaxies dominate at certain redshifts, that says something about merger rates and turbulent assembly. If compact massive galaxies are common in an era where they were expected to be rare, models must explain how so much star formation happened so soon, or why the mass estimates appear that way. The strongest science often lives in this tension between object and population. An individual galaxy gives the story a face. The population tells us whether that face belongs to a crowd. Webb's power is that it can do both, reveal intimate structure in selected objects and contribute to broad surveys that turn the early universe from a handful of curiosities into a measurable landscape. That landscape is not only made of galaxies, it also includes the dark spaces between them, where gas, radiation, and structure evolve on scales too large for ordinary imagination. During reionization, light from the first stars and galaxies help transform neutral hydrogen in intergalactic space into ionized plasma. This process did not happen everywhere at once. It likely unfolded in bubbles around luminous sources, with ionized regions growing, overlapping, and eventually filling much of the universe. Imagine dawn not as a single sunrise, but as countless lamps turning on inside a fog until the fog itself changes state. Webb helps identify the kinds of galaxies that may have contributed to that transformation. Small, numerous galaxies may have played a major role if enough of their energetic radiation escaped. Bright rare galaxies may also matter, but rarity limits their total contribution. The escape of radiation depends on the structure of gas and dust inside each galaxy. A dense, sealed system traps light. A clumpy, feedback-carved system may leak it. Once again, the mechanism hides inside the shape. This gives star formation a larger consequence. Stars do not only make a galaxy shine, their radiation can affect the space around galaxies. Their deaths can enrich surrounding gas. Their feedback can open channels through which light escapes. In the early universe, enough of this escaping radiation may have helped change the transparency of the cosmos itself. A star-forming galaxy is not only a local event, it can become part of a universe-wide transition. And yet, Webb does not let us pretend that all answers are easy. The question of which sources dominated reionization remains difficult. Faint galaxies are hard to measure, escape fractions are uncertain, dust complicates interpretation, the intergalactic medium absorbs light, models depend on assumptions. But Webb moves the uncertainty from vague speculation toward measurable constraint. It gives scientists more galaxies, better redshifts, more detailed spectra, and sharper views of the physical systems involved. That is what a great telescope does. It does not erase mystery, it gives mystery edges. Edges matter because they let us separate real surprise from theatrical surprise. A claim that the early universe contained luminous galaxies is interesting. A measured population of high redshift galaxies with estimated star formation rates, masses, colors, sizes, and spectra is more than interesting. It is a test of how matter behaved under conditions we cannot recreate on Earth. We cannot build a young universe in a laboratory. We can only collect the light it sent before we existed. There is something deeply strange about that. Human beings arrived impossibly late in cosmic history. Our species has existed for only a tiny fraction of the age of the universe. Modern astronomy, with its mirrors, detectors, rockets, cryogenic instruments, and data pipelines, is younger still. And yet, because light travels at a finite speed, lateness gives us access. We are late enough that ancient light has had time to reach us. We are brief enough that the fact feels almost impossible. Our delay became our window. Webb sits at that window and collects evidence that the universe has never been one thing for long. In one direction, dust-hide stars that infrared light can reveal. In another, redshifted galaxies carry signals from cosmic dawn. In another, a cluster's gravity bends background light into arcs. In another, a galaxy's spectrum hints at metals made by earlier stars. Each observation is different, but the lesson is the same. Matter remembers what happened to it. And because matter remembers, the universe can be read. And because matter remembers, the universe can be read, but never in a single language. Some memories are carried by light, some are carried by motion, some are carried by chemistry, some are carried by shape, a galaxy's color, its spectrum, its size, its surroundings, and even its silence all become parts of the same record. Webb is powerful because it can bring several of those records together, especially for objects so distant that older views turn them into little more than hints. One of the most important records is size. A galaxy's physical size tells us how concentrated its stars are and how quickly it may have assembled. Some early galaxies appear remarkably compact, with much of their light packed into small regions. A compact galaxy is not automatically impossible, but it forces a sharper question. How did so much star formation fit into so little space so early? Was the system fed by dense streams of gas? Was it shaped by mergers? Is some of the brightness coming from an active black hole? Are we seeing a brief intense phase rather than a long stable state? This is why a small-looking object can be more extreme than a large-looking one. In astronomy, apparent size can deceive. A nearby galaxy may sprawl across an image because it is close, while a distant massive system may be compressed into a faint dot. Webb's resolution helps, but distance still squeezes detail. To understand a galaxy's true size, astronomers combine its angular size with its redshift-based distance. Only then can the dot become a physical scale. Hundreds of parsecs, thousands of light-years, a compact core, an extended disk, or a disturbed system stretched by interaction. A parsec is about 3.26 light-years, which means even a galaxy only a few hundred parsecs across is still huge by human standards. A system with an effective radius under 500 parsecs would span more than 1,600 light-years across that central measure. That is larger than many human imaginations can hold, yet compact for a galaxy containing enormous numbers of stars. Scale is always relative in the cosmos. Something can be impossibly large to us and still compressed by galactic standards. Compactness matters because it changes the physical conditions inside the galaxy. Pack gas and young stars into a smaller region, and radiation fields intensify. Supernovae overlap more easily. Gas can be driven inward or blown outward more violently. A central black hole, if present and feeding, may influence a larger fraction of the surrounding system. Dense early galaxies may therefore evolve quickly, not only because they are young, but because their internal conditions are extreme. Their clocks are not faster in a literal sense. Their processes are more concentrated. This concentration may help explain why some galaxies seem to mature early. A galaxy does not need to be old by the calendar if its star formation was intense enough to build stellar mass quickly. It does not need billions of years of quiet growth if it lived through a short era of extraordinary efficiency. But that efficiency brings a cost. Intense star formation rapidly consumes gas, and the same massive stars that make the galaxy bright also inject energy back into the environment. A fast beginning can create the conditions for an early slowdown. This is one of the most elegant and unforgiving ideas in galaxy evolution. Success can become self-limiting. The faster a galaxy builds stars, the more violently those stars push back. The more gas falls inward, the more energy can be released by stars and black holes. The brighter the burst, the more likely the reservoir is being altered. In human terms, the galaxy is not simply growing rich, it may be spending its inheritance at a pace that changes everything afterward. This does not mean all early bright galaxies are doomed to fade quickly. Some may continue receiving gas from the cosmic web. Some may merge with gas-rich neighbors. Some may regulate themselves and keep forming stars over long periods. Others may truly burn through or lose much of their cold material. The diversity is the point. Webb is not revealing one fate. It is revealing the range of possible fates under early cosmic conditions. To see that range, astronomers compare galaxies across redshift. Redshift is often treated as a distance marker, but for evolution it becomes a sequence. At high redshift, we see earlier populations. At lower redshift, we see later ones. The comparison is never perfect, because we are not tracking the same individual galaxy from youth to old age. Instead, we are comparing populations across time, using models to connect ancestors and descendants statistically. It is like studying human aging by looking at many people of different ages, rather than watching one person for an entire lifetime. The method is indirect, but powerful. The risk is assuming too much continuity. A galaxy seen at redshift 7 is not simply the younger version of a galaxy seen nearby. It may merge. It may be destroyed as an independent object. It may become part of a cluster. It may feed a larger descendant. Cosmic genealogy is messy, but patterns still emerge. The average properties of galaxies change. The abundance of massive systems changes. The balance between star-forming and quiet galaxies changes. Shapes change. Chemical enrichment increases. The population becomes a record of transformation. Webb strengthens that record, especially at the faint end, where smaller galaxies may have been numerous and important. Bright galaxies are easier to find, but the faint ones may dominate certain processes because there are so many of them. During cosmic dawn, countless small galaxies may have contributed significantly to the radiation that ionized the universe, but faint galaxies are difficult to detect, and their properties are hard to measure. Webb pushes deeper into that hidden population, giving scientists a better chance to estimate how much work the small galaxies did. There is a lesson there beyond astronomy. The most important agents in cosmic history are not always the most visually dramatic. A giant galaxy cluster bends light spectacularly, but small galaxies may have helped change the state of intergalactic hydrogen. A brilliant quasar can dominate an image, but ordinary star-forming galaxies may have produced much of the radiation budget. A single record-breaking object can seize attention, but the quiet majority often carries the statistical truth. Webb's view is most powerful when it balances spectacle with census. This balance is part of why the telescope has become such a turning point. Hubble showed humanity that deep space was filled with galaxies at different stages of history. Webb continues that legacy, but moves deeper into infrared, where the earlier universe becomes more accessible. It can see through dust more effectively in nearby regions and catch redshifted light from distant ones. It connects the hidden birth of stars with the ancient birth of galaxies. It makes the local and the primordial feel like parts of one continuous physical story. And that continuity is the real evidence of cosmic evolution. The physics that collapses gas into stars nearby also operated long ago, under different conditions. The feedback that carves cavities in local star-forming clouds also has grander versions in galaxies. The chemical enrichment we see in young star systems around us depends on earlier enrichment in galaxies before us. The universe is not divided into separate miracles. It is one chain of mechanisms changing scale. The more Webb reveals, the less satisfying it becomes to say simply that the universe is old and large. Old and large are true, but too empty. The better truth is that the universe is historical. Its present condition depends on earlier conditions. Its structures carry memory. Its galaxies are not placed in space like decorations. They are outcomes. They have biographies written in light, gas, dust, stars, and dark matter. When Webb captures ancient infrared light, it gives us access to those biographies before the ending is known. It shows galaxies young enough that their later descendants may look nothing like them. It shows star formation intense enough to alter the future. It shows shapes unsettled enough to betray recent violence. It shows chemical traces that prove earlier generations of stars had already lived. And sometimes, it shows quietness where we expected growth, or maturity where we expected only beginnings. That is why the evidence feels like a living archive, not because the images move before our eyes, but because every stillness contains process. A red dot contains expansion, a spectrum contains chemistry, a distorted arc contains gravity, A clump contains collapse. A fading galaxy contains loss. A field of thousands contains the changing statistics of the universe. Webb has not made the cosmos less mysterious by measuring it. It has made the mystery accountable to reality. Accountable mystery is harder and more beautiful than mystery left vague. It asks the universe to answer with evidence. It lets a faint galaxy remain strange, but not shapeless. It lets a distant signal keep its uncertainty, while still placing that uncertainty inside gravity, light, gas, chemistry, and time. Webb's greatest discoveries live in that balance. They are neither ordinary nor magical. They are physical. And physical things have consequences. If early galaxies formed stars more efficiently than expected, then the first billion years of the universe were more productive than some models allowed. If black holes grew early inside some of those galaxies, then gravity may have created luminous engines sooner than we imagined. If dust appeared quickly, then the first generations of stars enriched their surroundings fast enough to hide later activity from visible light. If compact galaxies became massive early, then the densest places in the young cosmic web were able to concentrate matter with extraordinary speed. Each possibility changes the rhythm of the early universe. Notice the word rhythm. It is better than miracle. It suggests timing, pressure, repetition, and variation. The universe did not become complex by a single impossible jump. It became complex through processes that repeated under changing conditions. Gas fell in, stars formed, stars changed the gas, gravity merged systems, radiation escaped or was trapped, outflows removed fuel, new gas arrived, the same verbs return, but the stage changes each time. This repeated pattern is why Webb can connect a dusty stellar nursery near us to galaxies near cosmic dawn. They are not the same object, and they do not belong to the same era, but they share physical grammar. In both cases, gravity gathers material. In both cases, density matters. In both cases, light is partly hidden by dust. In both cases, young stars reshape the clouds around them. Local star formation gives us a close-up view of mechanisms that, at larger scales and earlier times, helped build galaxies themselves. The close-up view is essential because deep time can become abstract. A galaxy 13 billion light-years away is too far for the mind to touch directly. But a star-forming cloud, even one 1,000 light-years away, feels closer. We can imagine dust glowing in infrared. We can imagine jets from young stars cutting through surrounding gas. We can imagine dense filaments feeding new objects. Then, when Webb turns toward the distant universe, those local mechanisms become a kind of translator. The ancient galaxy is no longer just a red dot. It is a place where gas, stars, dust, and feedback were also negotiating a future. This is how good astronomy rescues scale from emptiness. It does not merely tell us that something is far, it tells us what is happening there, or what was happening when the light left. Far becomes specific, old becomes active, faint becomes meaningful. The same rescue happens with time. 13 billion years can become numb if it remains only a number, but place it beside a human life, and the scale begins to open. A person may live for 80 years. Recorded human history spans only a few thousand years. Agriculture reaches back around 10,000 years. The age of Earth is about 4.5 billion years. The universe is about 13.8 billion years old. By the time Earth formed, the universe had already lived most of its current life. By the time humans looked up with telescopes, ancient galaxy light had already been traveling longer than our planet had existed. That fact is almost too quiet to sound dramatic, which is why it matters. The evidence Webb collects did not begin moving toward us because we were here. It was already on its way when there was no Earth to receive it. It kept traveling while the solar system formed, while oceans condensed, while life began, while continents drifted, while mammals appeared, while human beings learned to make tools, languages, mathematics, mirrors, rockets, and detectors. The photon did not know any of this. It simply traveled, yet its arrival now allows the late universe to inspect its early self. This is one of the deepest emotional turns in the story. We are not watching cosmic evolution from outside it. We are made by it, delayed within it, and briefly able to understand it. The atoms in our bodies are not spectators. They are products of stellar and galactic history. When Webb studies ancient enrichment, star birth, and galaxy growth, it is not studying something separate from our existence. It is studying the long physical inheritance that eventually made observers possible. But inheritance is not destiny. The universe did not aim for us. Most of its space is lethal to bodies. Most stars are not suns like ours in the comforting human sense. Most planets, if they exist around a given star, are not Earth. The processes that make complexity possible are also indifferent to whether complexity survives. Radiation can sterilize. Impacts can reset. Supernovae can enrich and endanger at the same time. Black holes can regulate galaxies without caring what futures they erase. Cosmic evolution is creative, but not kind. That is why the calm tone matters. If we turn the universe into a monster, we distort it. If we turn it into a comforting story designed around us, we distort it again. Webb shows something more exact, a universe where matter follows laws, where those laws produce astonishing richness, and where life, if it appears, must do so inside conditions that were never guaranteed. The awe comes from truth, not flattery. And the truth is that Webb has made the old night sky feel historical in a new way. A dark patch is no longer merely a dark patch. With enough exposure, enough sensitivity, and the right wavelength, it may reveal galaxies at many ages. A red point may become an early star-forming system. A faint arc may become a lensed background galaxy. A dusty glow may become a hidden nursery. A spectrum may reveal that stars had already lived and died before the light began its journey. The night sky used to look timeless because human lives are short. Stars return with the seasons, constellations seem fixed, the Milky Way arches quietly. But this stillness is an illusion produced by our tiny slice of time. Give the universe millions of years, and stars move. Give it billions, and galaxies transform. Give it Webb, and the still image begins to confess the motion it contains. That confession does not arrive as noise or spectacle. It arrives as infrared light measured one wavelength at a time. It arrives as a galaxy catalogue, a redshift estimate, a spectral line, a distorted arc, a star-forming clump, a dust-obscured source, a compact core whose meaning is still being debated. It arrives through careful work, not instant certainty, but together, those pieces form one of the most profound sentences modern science can say. The universe has a biography, and we are learning to read the early chapters while their light is still arriving. The universe has a biography, and the strange thing is that its earliest chapters are not gone. They are only distant. Their light has been stretched, weakened, and delayed, but not erased. Webb's task is to catch that weakened light before it sinks below the limits of our instruments, then turn it into something human minds can understand: an age, a distance, a spectrum, a shape, a possible history. That possible history is always held with care. A galaxy's light may suggest rapid star formation, but star formation depends on assumptions about dust, stellar ages, and the initial mix of stellar masses. A galaxy may appear massive, but mass estimates can shift when better spectra arrive. A source may seem extremely distant, but photometric redshift can be fooled by dusty nearer objects or unusual spectral features. This is not a flaw in the story. It is the discipline that keeps the story honest. The universe is allowed to be surprising, but not allowed to be whatever a headline wants it to be. Webb's strongest impact comes from narrowing the space between surprise and explanation. Before Webb, many early galaxies were beyond reach or blurred into uncertainty. After Webb, more of them have colors measured across infrared filters, shapes resolved at finer scales, and spectra strong enough to anchor their redshifts. The result is not a single answer shouted from the darkness. It is a tightening net of evidence. The young universe is becoming harder to describe vaguely. And the more precise the description becomes, the more alive the early cosmos appears. There were galaxies gathering in dense regions. There were stars forming in clumps. There were metals appearing after earlier stellar deaths. There were black holes possibly feeding in some compact systems. There were winds pushing gas away. There were mergers bending shape and triggering bursts. There were small galaxies that may have been numerous enough to help change the state of intergalactic hydrogen. This is not stillness. It is activity seen through delay. One of the most powerful ideas here is that delay does not turn action into fiction. When we see a galaxy as it was 12 or 13 billion years ago, that phase is not happening now in the galaxy's own local present, but the light from that phase is happening now for us. The evidence arrives now, the measurement happens now, the understanding is built now. Cosmic time is not shared evenly across distance. It reaches us in layers. And Webb is letting us touch those layers with instruments instead of imagination. This layered time also changes how we think about the word ancient. Ancient, in human life, usually means dead, buried, finished. Ancient ruins no longer host the civilization that built them. Ancient bones no longer belong to a living body. But ancient light is different. It is old because it began traveling long ago, yet it is active because it is still arriving. The photon has crossed space without becoming a memory in the ordinary sense. It is the original messenger, not a copy. When Webb detects it, the past does not return. The past completes its journey. That completion is almost impossible to feel all at once. A photon from a high redshift galaxy may have left before the Milky Way had its present form, before the Sun existed, before Earth was a planet, before the carbon in your body had been gathered into a living cell. It moved through an expanding universe while space itself stretched the wavelength it carried. It passed through regions shaped by gravity, sometimes near massive structures that bent its path. Then it reached a telescope whose mirror unfolded in space because a species on one late-forming planet wanted to know where it came from. Webb's evidence of cosmic evolution is therefore both technical and emotional. Technically, it lies in redshifts, spectra, morphologies, stellar masses, star formation rates, dust estimates, lensing models, and galaxy catalogues. Emotionally, it lies in the realization that change has been traveling toward us since before there was an us. We did not invent the story. We arrived late enough to receive pieces of it. The early universe was not an empty waiting room. It was a dense, hot, changing environment where small advantages could grow quickly. A region slightly richer in matter could become a stronger gravitational well. Gas could fall in. Cooling could allow collapse. Stars could form. Massive stars could die quickly, enriching and disturbing their surroundings. If more gas arrived, the cycle could continue. If too much energy pushed back, the cycle could stall. This is the engine Webb keeps finding in different forms: gather, ignite, enrich, resist, repeat. That engine creates diversity. Some galaxies become bright because they are forming stars rapidly. Some become red because their light is stretched by distance. Some become red because dust hides their blue light. Some become quiet because their gas is gone or unavailable. Some become distorted because gravity from neighbors has pulled them out of shape. Some become magnified by foreground mass, letting Webb see what would otherwise remain beyond reach. A single image can contain all of these possibilities at once, which is why interpretation must be as careful as observation. Carefulness, though, does not make the story cold, it makes it stronger. When a narrator says, "This may be what is happening, and here is why scientists think so," the viewer is invited into reality rather than pushed into belief. The universe becomes something we approach with humility. The mystery is not a curtain hiding magic. It is a frontier where evidence is still arriving. That frontier now reaches into a period when the universe was young enough that every confirmed galaxy becomes historically valuable. Each one helps answer how quickly the first structures formed, how bright they were, how much dust they contained, how rapidly they made stars, and whether their radiation could escape. One galaxy alone cannot answer all of that, but thousands, then tens of thousands, then hundreds of thousands, across surveys begin to outline the evolution of the population. The biography becomes less fragmentary. And yet, even as the biography improves, it never becomes simple. The same universe that builds spirals also builds ellipticals. The same gravity that gathers matter also drives mergers that erase smaller systems. The same stars that create elements also produce feedback that can shut down future stars. The same black holes that seem like endings can regulate the growth of entire galaxies. Cosmic evolution is not a staircase. It is a branching river, constantly dividing, merging, drying, and flooding again under the pull of physical law. That is why Webb's view feels so different from a human history book. Human history is written around intentions, choices, conflicts, and memory. Cosmic history has no intentions. It has conditions. It has density, temperature, radiation, pressure, angular momentum, chemistry, and time. Yet from those impersonal conditions comes a universe rich enough to produce galaxies with biographies, stars with life cycles, planets with climates, and, at least here, minds that can ask what it all means. This is the quiet center of the title. Webb captured evidence of cosmic evolution not because it watched one object change in front of our eyes, but because it revealed that change is built into the evidence itself. The light is old because space is vast. The light is red because space expanded. The galaxies differ because matter changed under different conditions. The spectra contain metals because stars lived and died before them. The shapes are disturbed because gravity rearranged them. The silence of some galaxies exists because fuel became unavailable. Every observation points to process. And process is the true motion hidden inside a still image. And process is the true motion hidden inside a still image. That is the reason Webb's deep fields can feel motionless at first, then slowly become overwhelming. Nothing in the frame seems to move. The galaxies hang there like sparks suspended in black glass. But once you understand what the light means, the stillness dissolves. One point is a young system forming stars. Another is a galaxy bent by gravity. Another is a cluster seen billions of years ago. Another is an ancient source whose light has crossed most of cosmic history. The image does not move because our lives are too short. The universe is moving anyway. This is the scale difference that humbles every attempt to make the title sound simple. A human can watch clouds change in minutes, a child grow in years, a forest mature in decades, a city transform in centuries. But a galaxy lives on clocks so vast that even civilization is too brief to watch the full story directly. If we waited 10,000 years, the nearest galaxies would look almost the same to ordinary eyes. If we waited 1,000,000 years, some stellar motions would become measurable in a grander way, but galaxy evolution would still be slow. To see cosmic change, we need another method. The universe gives us that method through distance. It lets us look at many clocks at once, because every faraway object shows us an earlier reading of its own clock. This is not a trick. It is a consequence of finite light speed. A telescope becomes a time machine not because it breaks physics, but because it obeys physics exactly. The farther the source, the older the message. The older the message, the earlier the stage of cosmic evolution we can inspect. So Webb's evidence is not a single captured transformation. It is a vast comparison made possible by delayed light. Here are nearby star-forming regions where stars are being born inside dust. There are galaxies from billions of years ago when cosmic star formation was more intense. Farther still are young systems from the first billion years, glowing with early activity. Across them all, the same question repeats in different accents. What is matter doing under these conditions? Sometimes it is gathering, sometimes it is cooling, sometimes it is igniting, sometimes it is colliding, sometimes it is enriching itself, sometimes it is losing the very fuel it needs to continue. That range is what makes the evidence feel alive. Cosmic evolution is not one upward arrow. It is a field of physical negotiations unfolding across environments and eras. And perhaps the most important negotiation is between formation and feedback. Without formation, galaxies would remain dark reservoirs of gas. Without feedback, they might grow in ways that do not match the universe we observe. Feedback is the corrective pressure, the pushback created by the very stars and black holes that galaxies produce. It can heat gas, stir gas, expel gas, or prevent new gas from cooling. It can make galaxies less efficient. And that inefficiency may be exactly what allows the cosmic population to look the way it does today. This is a deeply counterintuitive idea. We often imagine creation as an unlimited positive force. More gas, more stars, more light, more galaxies. But the universe we see is shaped by limits. Too much cooling without resistance would overbuild galaxies. Too much resistance would leave them underbuilt. The observed universe exists between those extremes. It is not just the product of gravity winning. It is the product of gravity being answered. Webb is helping us hear that answer earlier than before, in the young universe, where gas densities were high and galaxies were compact. Feedback may have been especially dramatic. Star formation in dense clumps could drive strong winds. Early black holes, if present, could add energy from small central regions. Mergers could funnel gas inward and trigger bursts that later helped clear material out. In a compact system, the distance between cause and consequence shrinks. A burst of star formation does not merely brighten the galaxy, it can help reshape the conditions for everything that follows. That is why an outflow in a distant galaxy is not a side detail. It is a sign that the galaxy's future is being negotiated. Gas moving outward may later fall back, enriching a halo and feeding later star formation. Or it may escape the galaxy's grip, removing fuel permanently, or it may heat surrounding material so that cooling becomes difficult. The same observed wind can carry several possible futures, depending on mass, speed, environment, and time. Webb's data can show the evidence. The interpretation must ask what the evidence can physically become. This future-oriented thinking is strange because we are studying the past. A galaxy seen as it was 12 billion years ago has already had 12 billion years to change. Yet the phase Webb observes still matters, because it shaped the path to whatever descendant exists now. If that early galaxy merged, its stars became part of something larger. If it lost gas, its descendants inherited that loss. If it enriched its surroundings, later generations formed from changed material. A past state is not dead information, it is a cause. The same is true for the universe as a whole. The early rate of star formation affected how quickly heavy elements spread. The escape of radiation affected ionization. The growth of black holes affected galaxy centers and surrounding gas. The assembly of dense regions affected cluster formation. Tiny differences in the young universe became the large structures that later telescopes would map. Cosmic evolution is cause preserved across billions of years. This is why the Webb era feels historically important. It has arrived after more than a century of humans learning that the universe is larger, older, and more dynamic than our ancestors imagined. We learned that the Milky Way is not the whole cosmos. We learned that galaxies are separate systems. We learned that the universe expands. We learned that distant light reveals earlier time. We learned that stars make the elements. We learned that galaxies grow, merge, and sometimes stop forming stars. Webb did not invent these ideas. It has given us a sharper way to test them near the beginning. That distinction matters. A great telescope is not valuable because it makes every older telescope obsolete. It is valuable because it extends a chain of seeing. Hubble changed our emotional relationship with deep space, showing galaxies scattered across tiny dark fields and revealing that the early universe was already rich. Webb takes that inheritance into longer infrared wavelengths, where the earliest galaxy light has been stretched, where dust becomes more transparent, where hidden star formation can be revealed, and where ancient structure can be measured with new clarity. It is not a replacement for the past, it is the next layer of the eye. And the next layer has made the old sky feel young again. Not young because the universe itself is young now, but because the evidence of its youth is arriving with such force. Every confirmed ancient galaxy adds another fixed point to the map. Every uncertain candidate invites sharper follow-up. Every spectrum strengthens or weakens a possible story. Every survey moves us from anecdote to population. The early cosmos is no longer only a theoretical landscape drawn from equations and simulations. It is becoming a measured place, one faint object at a time. Still, the more we measure, the more careful the wonder becomes. Some early galaxies are real surprises. Some are less extreme after better analysis. Some apparent tensions soften when dust, lensing, black holes, or star formation history are treated more carefully. This does not reduce the drama. It makes the drama mature. The universe does not need every candidate to be shocking. It only needs enough confirmed evidence to show that our older picture was incomplete in specific ways. Specific incompleteness is the engine of progress. It says, here is where the model worked, here is where it strained, here is where the data sharpened the question. Maybe early star formation was burstier than expected. Maybe compact galaxies were more common. Maybe feedback operated differently in dense young systems. Maybe black holes grew rapidly in some environments. Maybe galaxy shapes emerged earlier in certain regions. Each possibility is not a slogan, it is a research path. And behind every research path is the same quiet realization. The universe is not finished explaining itself. The photons Webb catches have completed their journeys, but our understanding of them is still forming. In that sense, cosmic evolution continues not only in galaxies, but in knowledge. The ancient light arrives, instruments measure it, human minds interpret it, models change, questions become sharper, reality becomes clearer, and then stranger again. This is the calm aftershock of Webb's evidence. The telescope shows us that the universe's past is not locked away beyond reach. It is faint, stretched, delayed, and difficult, but it is not silent. It keeps arriving in the dark. It arrives as infrared light from galaxies whose descendants may now be unrecognizable. It arrives as dust glow from stars being born in our own galaxy. It arrives as arcs bent by gravity and spectra, marked by elements forged in vanished stars. It arrives carrying the long memory of matter becoming more than it was. It arrives carrying the long memory of matter becoming more than it was, and that may be the most accurate way to understand what Webb has captured. Not a simple cosmic video, not a single galaxy visibly aging before us, not a miraculous shortcut around the vastness of time. Webb has captured memory in motion, photons that left ancient galaxies when the universe was young, photons from dust where stars are forming now, photons bent by gravity, reddened by expansion, marked by chemistry, and finally gathered by a telescope built by a species that appeared almost impossibly late. The final lesson is not that the universe changes. That part is easy to say. The deeper lesson is that change leaves evidence, and evidence can travel. A star can die and enrich a cloud. A cloud can collapse and form new stars. A galaxy can merge and hide the history of smaller systems inside its halo. A black hole can feed and heat the gas around it. A burst of star formation can brighten a galaxy while weakening its future supply. These events may pass, but they are not simply lost. Their consequences remain in light, motion, structure, chemistry, and silence. Silence matters too. A quiet galaxy is not empty of story. It may contain billions of old stars, each one a remnant of earlier formation. It may have lost the cold gas needed for renewal. It may have been shaped by feedback, environment, or time. From far away, it can look serene, but serenity can be the surface of an exhausted history. In the same way, a dark patch of sky is not necessarily empty. It may be filled with faint galaxies beyond the reach of a given exposure, or with gas too diffuse to shine brightly, or with voids that reveal how unevenly gravity built the cosmic web. Webb teaches us to distrust the first impression of stillness. The sky is still only because we are brief. The stars seem fixed because a human life is too short to watch their grander motion. Galaxies look suspended because their changes take longer than civilizations. But the evidence is everywhere once we learn how to read it. Spiral arms trace rotation and density waves. Stellar populations trace age and enrichment. Dust traces earlier generations of stars. Redshift traces expansion. Lensing traces gravity. Outflows trace struggle. Quenching traces the disappearance of future birth. And all of it returns to the first broken intuition. A telescope image does not simply show where things are. It shows when their light began traveling. The moon is a second old to our eyes. The sun is 8 minutes old. Nearby stars are years or centuries old. Distant galaxies are millions or billions of years old. The deepest Webb targets carry light from a universe still forming its first great structures. The farther we look, the more the present dissolves into a layered archive. That archive does not make us masters of the universe. It makes us careful witnesses. There is a difference. A master imagines control. A witness receives, studies, and tries not to distort. Webb cannot command galaxies to reveal themselves fully. It cannot remove every ambiguity. It cannot tell us the whole life of every faint source. But it can gather enough ancient light to force better questions. It can show that some early galaxies were brighter, denser, dustier, more active, or more mature than simple expectations allowed. It can reveal that cosmic evolution was not a slow decorative unfolding, but a physical negotiation already intense near the beginning. The negotiation continues today. Stars still form in the Milky Way. Gas still moves along galactic structures. Andromeda still approaches. Dwarf galaxies still fall into larger halos. Black holes still feed in some galaxies and sleep in others. Galaxy clusters still bend light. The cosmic web still holds matter in filaments and nodes. The universe is older now, cooler now, quieter in its star formation than it once was, but not finished. The fire has lowered, it has not gone out. That matters because we often imagine the universe as either remote or complete. Remote because its distances are unbearable. Complete because the night sky looks ancient and still. Webb breaks both assumptions. The universe is remote, but its light reaches us. It is ancient, but its evidence is active. It is not complete in the sense of being frozen. It is a history still unfolding, with every present condition shaped by earlier ones, and every new observation reshaping what we understand. Somewhere in that history, the atoms that make us were forged. Somewhere, stars died before the sun existed. Somewhere, gas enriched by older stars gathered into the cloud that became our solar system. Earth formed from that material. Oceans appeared. Chemistry became biology. Life became awareness. Awareness became a question. And eventually that question built instruments capable of seeing the faint infrared glow from galaxies older than the planet that asked. There is no need to turn this into destiny. The universe did not arrange itself for our comfort. It is too vast, too indifferent, too full of harsh radiation, vacuum, heat, cold, collapse, and loss for that. But there is still a quieter meaning available. We are not central, but we are present. We are not the purpose of cosmic evolution, but we are one of its consequences. We are made of matter that learned, through stars and time, to ask about matter. That is why Webb's evidence feels different from an ordinary discovery. It does not only add another object to a catalogue, it alters the emotional shape of the sky. After Webb, a red dot can no longer be dismissed as a red dot. It may be a galaxy from cosmic dawn. A smear of light may be a merger. A faint arc may be a background system magnified by gravity. A dusty glow may be a hidden nursery. A quiet galaxy may be a record of fuel lost and star formation ended. The image remains still. But the stillness is crowded with causes. So when we say James Webb captured evidence of cosmic evolution in real time, the most honest version is also the most beautiful. It captured real light, arriving now from real stages of cosmic change. It captured the universe building stars, assembling galaxies, enriching matter, bending light, disturbing shapes, losing fuel, and preserving its own history across distance. It captured not one moment, but many moments meeting in our present. And as the telescope keeps watching, the archive will grow. Some early candidates will be revised, some surprises will fade, others will harden into new understanding. The models will change, not because science is weak, but because science is alive enough to listen when reality speaks more clearly. Webb's deepest gift is not certainty without effort. It is a sharper relationship with truth. At the end of the journey, the night sky looks almost the same to the naked eye. Dark above us, quiet, familiar. But something underneath has changed. The darkness is no longer empty. The stillness is no longer still. Every faint light is a time-delayed witness. Every galaxy is an unfinished sentence written by gravity, gas, stars, and loss. And somewhere in that vast, patient archive, ancient photons are still crossing the dark, carrying the memory of a universe that was already becoming. Long before we were here to receive it,